Have you ever just stopped and thought about how weird our planet is? I mean, we've got these scorching hot deserts and at the exact same time, these massive frozen ice caps. Kind of strange, right? Well, today we're going to take a tour of Earth's temperature to figure out the rules that make our world hot, cold, and yeah, sometimes completely upside down.
So, seriously, how is this even possible? The answer, as you might guess, isn't just one simple thing. It's really a journey that takes us all the way from the sun-baked equator to the frigid poles, and then from the ground we walk on, right up to the very edge of space.
So here's our game plan for this little tour. First, we're going to look at the biggest, most basic rule that decides temperature across the whole globe. Then, we're heading up to see what happens when you climb higher and higher. After that, we'll get into a really bizarre exception where the rules just get flipped on their head. And finally, we'll tie it all together and see why this stuff really matters for our everyday weather and our planet's future.
All right, part one. Let's get right into it with the first big rule: why are some parts of our planet just naturally hotter than others? You know, it really all boils down to the angle of the sunlight. The area right around the equator, what we call the torrid zone, gets hit by the sun's rays pretty much head-on all year long. That's why it's so hot. But the farther you move away from the equator, the more that sunlight gets slanted, creating those milder temperate zones, and eventually the icy cold frigid zones at the poles.
Okay, here's a super simple way to picture this. Imagine the sun is a giant flashlight. At the equator, that flashlight beam is shining straight down, so all its heat is focused in a small, intense circle. But because the Earth is a sphere, as you move toward the poles, that same beam gets smeared out over a much bigger area. It's the exact same amount of energy, but it spreads super thin, and that's why it's so much colder up there.
But of course, it's not that simple. The sun's angle is just the starting point. There are four other huge factors that kind of mix together to create the climate right where you live. You've got your latitude, obviously. Then there's the fact that land heats up and cools down way faster than the ocean does. You've got these massive ocean currents acting like a global plumbing system, moving heat all over the place. And finally, topography, the shape of the land, mountains, valleys, that can create its own tiny, unique weather patterns. And if you want to see just how big a difference this makes, look no further than the Gulf Stream. This is a massive river of warm water flowing from the tropics all the way up to Western Europe. It is the single reason that London has relatively mild winters instead of brutally cold ones like you'd find in Siberia, even though they're at similar latitudes. It's a perfect example of the planet's heating and cooling system in action. Okay, so that's the rule for traveling across the globe. But what about traveling up? What happens to the temperature as you go higher and higher into the sky? Now, you might just think it gets colder the higher you go, but it's a little more complicated than that. See, our atmosphere has layers. We live way down here in the bottom one. It's called the troposphere. This is where basically all of our weather happens, and in this layer, the rule is pretty clear. The higher you go, the colder it gets. And get this, there's even a number for it. On average, for every 1,000 meters you climb up, the air gets about 6.5 degrees Celsius cooler. It's called the environmental lapse rate, and it's the simple reason why mountaintops are covered in snow even in the middle of summer.
But hey, rules are made to be broken, right? Sometimes our atmosphere just decides to flip this rule completely on its head, and when it does, it creates a phenomenon that has some really major effects on all of our daily lives.
This is what we call a temperature inversion, and it's exactly what it sounds like. Everything's inverted. Instead of getting colder as you go up, for a certain stretch, it actually gets warmer. What you have is a layer of cold, heavy air trapped on the ground with a lid of warmer, lighter air sitting right on top of it. You can really see the difference here. On a normal day, the warmer air near the ground can rise up, carrying pollution and dust away with it. But when you have an inversion, that cold air is stuck. It's trapped by that warm lid above it, and nothing can escape. So how does this whole upside-down thing even happen? Well, it usually starts on a clear, calm night. When there are no clouds to act like a blanket, the ground radiates its heat straight out into space and gets really cold really fast. This chills the layer of air right above it, making it colder than the air higher up. And boom, just like that, you've got yourself a temperature inversion. And this is a big deal. Inversions are the reason why some cities get those really thick, nasty smog days. The pollution literally has nowhere to go. They also cause that dense morning fog that can snarl traffic and delay flights. But here's a weird twist. It's not all bad.
And inversion can actually protect crops by trapping a layer of slightly warmer air near the ground, saving them from a deadly frost. It can even make sounds travel much farther than they normally would.
So, we have our rules, right? One for across the globe, one for going up, and the crazy exception that breaks them. But why does understanding all this actually matter right now? Let's connect the dots. The key idea here is something called a temperature anomaly. It sounds complicated, but it's really simple. It's just the difference between the actual temperature and the long-term average for that specific place and time. When scientists talk about climate change, they're often tracking these anomalies. A whole string of positive anomalies, or hotter than average periods, is a really clear signal that the entire system is warming up. And these positive anomalies aren't just numbers on a spreadsheet. They have devastating real-world consequences. We've seen this again and again with major heat waves in recent history, from the deadly 2003 event in Europe to the record-shattering heat dome that sat over the Pacific Northwest in 2021. These aren't just hot days. They're extreme events that push our infrastructure, our agriculture, and our own health to the absolute limit. And all of this leaves us with one really big question. We've just explored the basic fundamental rules of our planet's temperature. But what happens when the planet itself starts to change? How will these fundamental rules, the very physics we just talked about, begin to shift as the world gets warmer? That, right there, is the challenge we all face now. Thanks so much for joining me on this tour.